So in the modified Bohr theory, we assumed a particle which is much more heavier than the electron, but the charge was same as the electron. So imagine if we have a particle which is not electron but some, let's say, mesons. Okay. You can also represent by pi. So we have pi mesons and other mesons also. And it is having the charge same as, so charge is same as electron, but mass is 200 times the mass of electron. So you can say mass of meson is roughly 200 times the mass of electron. And in that case, what I said, the motion will happen around the common center of mass, right?
Yes.
So if you consider the nucleus and this new charged particle, and r is of course the distance of the particle from the nucleus. So if I call the mass here as m, this mass as small m, so we will have center mass somewhere here, right? And therefore, both will be moving in the concentric circle.
Yes, sir.
Around the common center mass. So this one and this one. So how to proceed with the question here? So Coulomb force will remain same, right? So the charge here is ZE, the charge here we are assuming E only, minus E. So the force of attraction will not change, correct? So force of attraction, you can say Coulombic force will be same. K ZE square by R square. So there is no change in the Coulomb force, so that equation remains unchanged. Now the angular momentum. So earlier we were writing the angular momentum for the particle itself, the electron itself. And so we were writing MVR. I hope you remember this. Now, should we write MVR now also? So if you write MVR, will it be correct? Tell me, yes or no? The angular momentum of this system, because we are talking about the angular momentum of system earlier, nucleus was at rest, so the angular momentum was only associated with the particle, that is moving particle, that is electron. Now we have both electron and the nuclei both moving, and therefore both will contribute to the angular momentum. And therefore we have talked about something called angular velocity omega. Okay. So as the electron will move away, omega will definitely change. You can call omega n if you wish to call. You can call Rn if you wish to call. So how to write the angular momentum part? Tell me. L will be equal to how much? Tell me, guys, what is angular momentum in this case? L is equal to so both are moving in a such a way that the separation is constant, and the orientation is the relative orientation is also constant. So we can treat as a rigid body, because the separation is not changing. So once you treat two mass system as a rigid body, you can write the angular momentum as I of the body into omega. It is clear?
Yes,
Now
sir.
the question is how to write I. What is the moment of inertia of the system? So I will be replaced by ICM because both are moving with.
Sir,
So
mu Rn,
yeah, tell me.
mu Rn square. Mu is the reduced mass.
Yeah, so mu Rn square and mu is the reduced mass, and that is equals to product of mass upon
Sum of
summation of mass. Correct. So this is the new moment of inertia, and now you can get the complete L value. So L we can write as mu omega n Rn square. So whenever you have the rotating system, then you have to write the L in this format, mu omega R square. So writing the angular momentum is not difficult, and then we can add the Bohr's second postulate. So what is the Bohr's quantization theory?
L equal ns by 2 pi.
Which means from theory and 4, you can add mu omega n Rn square is nh by 2 pi. You can see every question that we started with will start getting modified. So the MVR was nh by 2 pi. Now it is mu omega n Rn whole square. The next question is how to write the kinetic energy. So what is the kinetic energy of system? So in rotation, we write the kinetic energy of a system which behave as a rigid body as
Half I omega square.
half I omega square.
I see.
So if we substitute the value, the I was mu R square, and this will become omega n square. And we can replace in terms of Rn, because you can see, so you can add omega n equals to how much? nh by 2 pi mu. So 5 implies omega n equals to, let me add down. So the angular momentum is quantized, so mu into omega n Rn square equals to nh by 2 pi. So we can replace omega n from here. So omega n is how much? nh by 2 pi mu Rn square. And if you substitute here, the k becomes how much? Half and it is n square h square upon 4 pi square mu square Rn power 4, right?
Yes.
So the kinetic energy turns out to be how much? We can simplify, one mu will cancel out, Rn square will cancel out, n square h square upon 8 pi square mu Rn square. Correct? This is the kinetic energy.
Yes.
yes.
Okay.
Yes.
So in case of rotation or rotating, you can say system, the kinetic energy will take a format like this. Okay. And what about the potential energy? Potential energy was how much? So in potential energy, we talk about the electrostatic potential. We don't talk about the gravitation. So if you write the electrostatic potential, can write as minus k z square by Rn. I hope this is clear.
Yes, sir.
Okay. Okay. So we have written every formula. Moment of inertia is done. Okay, omega we have replaced. So now we need to write the the total energy. And before that, we need to write the okay. One more equation. The equation of circular motion for any individual particle. So you can write the circular motion for either small m or capital M. So for that, you need to know the radius of each particle. What is this radius, by the way? What is this radius? Tell me, guys. This radius is how much? So what are the values of R1, R2? You know how to find center mass for the two masses. What is R1? What is R1? Tell me.
MR by
Capital M
MRN by
upon M plus
capital M.
M into Rn
So R1 is capital M by M plus M
into
into
Rn.
Rn. Correct. So R1 is sufficient. You can also write R2, which is small m Rn by. So now what we can do next is we can write the equation of circular motion. So from circular motion dynamics, the net force is K ZE square by Rn square, and net force goes to, we can add M omega square R. You can say R1 because for M it is R1. So your equation will again look similar. Capital M by M plus M Rn. So it looks like again what? Mu omega square Rn. You can always remember these formulas or these relation. Okay. So this is the relationship between the kinetic and circular motion, and I think that will help us in getting the kinetic energy formula in terms of Rn. Okay, that will help. You can call it question number 6. So kinetic energy is how much? Once again, we can add mu Rn square omega n square and mu Rn square omega n square we can write as ZE square by mu Rn cube. Yes, this will cancel out completely, and the kinetic energy turns out to be how much? Oh, mu will get cancelled now. It is coming the same answer, KZE square by 2Rn, and this is what we were expecting, isn't it? Because we know that potential, half of the potential is the kinetic energy. So whether we have a single electron moving around the nucleus or whether we have a system of particles moving around the common center mass, the relation that we obtained earlier, that what we obtained earlier, if you remember, K was minus U by 2 and total was U by 2. That relation is still valid. It is clear. That relation is still valid. So the total you can write as also, that's why you can say the total is also minus K by 2. No, not 1/2. It's minus K just. So the total you can write as minus K. Can we write like this? Yes or no?
Yes.
Yes,
So it
sir.
is just a negative sign. So now the kinetic energy we have already obtained. We have the kinetic energy formula. So the total is available to us. Okay. Okay. What I can do is we need to find the Rn first. First we'll find the Rn. So now we are going to use this relation. Let's call A. This is called B. Why am I writing A and B? Because both are representing kinetic energy. So one is answer in terms of principal quantum number, and other we have derived using the dynamics, circular motion dynamics, because both are representing the kinetic energy, so they must be same. So your next step is simply equate it. So from A and B, what we can write? So from A and B, tell me guys, what do we have here? N square by 8 pi square mu r n square. Tell me if I'm wrong somewhere. 8 pi 8 pi square. And other question, what we're getting? K is ZE square by 2Rn. Okay, so this Rn gets cancelled. N square H square by 4 pi square mu Rn equals to is ZE square by 4 pi epsilon naught. This also gets cancelled. So Rn turns out to be how much? Epsilon naught M square H square upon pi is remaining mu is ZE square. So Rn turns out to be epsilon naught H square by mu pi E square N square by Z. Now, can you recall the old formula when nucleus was at rest? It was similar formula. The only difference was the mass was now replaced by
Mass of electron.
reduced mass. That is why you're not supposed to, derive this formula once again. But this is just for you to understand that everything can be converted. So that's why the derivation is lengthy. But once you remember that, if you know the basic formula, if you know the formula from the Bohr's atom, the only replacement is everywhere, wherever you see a small m, the mass of electron replaced by the reduced mass. Your job is done. You can check your notes. Do you have your notes? The last lecture?
Yes.
Check. It must be same.
Yes, sir.
It is same. With the only difference?
Mass of its reduced mass.
So the symbol m is replaced by
Mu.
reduced mass.
Mu.
Mu. So that's why you're not supposed to re-derive everything. You derive once for your learning purpose, but once you realize that, okay, everything can be created or recreated once we know the conversion factor. So mu will come into picture. And that is why I told you that the Rydberg constant. So the R infinity, and there was a formula for R infinity. Do you remember what was R infinity? Anyone? Tell me R infinity. The Rydberg constant. You can check the notes. It is there.
Sir, in terms
But
of
around
mu.
10 raised to 7.
No. In terms symbolically, what we derived.
Sir, in terms of mu.
No. R infinity cannot be in terms of R infinity only, I'm saying.
Okay.
The actual Rydberg formula that we derived from the Bohr's theory.
M e raised to 4. That
Is it
one?
like this or like this?
No. M e raised to 4, like E. electron one.
Mhm.
Uh, uh, upon 8 epsilon naught square
H
h
square.
cube c.
Correct.
Huh.
So this is the R infinity. So if I want to replace for the new kind of atom R mu, what will be? So R mu will be mu e power 4 because the charge we have kept same.
Yes.
So this is the conversion factor which you need to remember, because most of the time you will be knowing the R infinity and R mu can be derived. So R mu upon, and now you remember why we call R infinity. It means when the nucleus is infinitely heavy, which means it is not at all moving, and the ratio is mu by m. M means m. So your job is to express the answer in terms of R. So for example, if you remember the spectral line formula, 1 by lambda equals to how much? R
R
infinity
infinity z square
z square into,
1 by m square.
correct?
Yes.
So in this
Yes.
case, this is the old. So the new will be how much? R mu. But because R mu is not known to us, we are only knowing the R infinity. So we can replace R mu by. So the factor will come, and the factor is, so let's change the symbol also. That looks better. And what is interesting here to know that 1 by lambda mu is mu by me, and the rest was earlier present. So can we say this is 1 by lambda?
Yes.
So you can again see that, okay, we have something, a relation. The lambda mu is lambda by mu by me. So if you know the wavelength, so they'll tell you that, okay, let's say for a given transition, if the wavelength is this, now you imagine that the nucleus and the new charge particle are moving around the common center mass. If they also undergo similar transition, then what will be the new wavelength? Okay, so the new wavelength is going to be what? Less than or more than? Let's say if we consider that the same electron and the nucleus is revolving around the common center mass, the new wavelength will be, what will happen? Will it increase or decrease? The reduced mass is always less than the least value.
Yes, sir.
Yeah.
So if you have nucleus and if you have electron, the reduced mass will be less than mass of electron. No, not getting it. Are you getting it what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
So what you are supposed to do in Bohr's theory, in case of rotational dynamics is applied into the Bohr's theory, every formula which you derive like, the way you derive normally. At the end, replace m by mu. And because the readable constant is proportional to the mass, so R infinity will be proportional to a mass of electron, but the R mu will be proportional to mu. So if you remember this fact itself, you will get the answer for new derivation. Okay. So I hope we are done with the Bohr's theory, right? But still you haven't practiced even a single question. So we'll start doing problem first. So you all open the SVRMA, everyone? You all have SVRMA ready?
Yes.
sir. Yes.
Okay. So see, there are two ways to study modern physics as a beginner, because I'm not always with you. One is you can solve each and every question of the solved example of SVRMA, because that is really nice. Okay. But that you will do at home. So you will start with the exercise. Okay, it is just a matter of practice. Once you start doing it, you'll get the flow, and once you get the flow, you can solve every question. So you all start with the question number 1 of exercise 1. Everyone. You start from very basic. So how many of you practice the derivation part, which we did in the last lecture? Tell me honestly.
Yes.
Very good. Anybody else? Okay, so go ahead and solve the first question. The Bohr's radius is given by this formula. Verify that RHS has dimension of length. Oh, that's a nice question. Can you verify? You know the dimension?
Yes, sir.
Okay, go ahead and verify it. In JEE Advanced, if they ask you a question from the unit and dimension, which they do ask sometime, they will only ask from the modern physics part or thermodynamics part. Okay, so you have to be smart enough to solve this in quick, real quick. So you have to manipulate in a different way. Do this. So pi is constant, so you can ignore. Then we have mass. Okay. And what is the best way to replace epsilon naught in terms of fundamental mechanics or mechanical quantity? The best way is where you see the epsilon naught, very common.
Electrostatics.
Very good.
Electrostatic.
So replace it quickly by the Coulomb's law. If you understand, you will get the idea very quick. Done. That's too much for one question. So we have to prove that this dimension is length. So you can write as 4 equals to F equals to Q square by, just add the symbol, not the constant. So basically, epsilon naught by Q square is 1 by FR square. So basically, this is 1 by FR square, and then we have H square by M. And from here, it's very easy because you can add H into frequency square upon frequency square. So the H into F becomes the energy. So HF into energy. I mean, this is energy square. So energy square and force into displacement is also energy into R into. So one energy gets cancelled. And then we have energy into time square basically. So hopefully from here it's easy to get the answer, right? Again, you can say energy upon R is
Yes.
force. It's Ft square by m. And force per mass is equal acceleration. So it's AT square, and we know half AT square is. It's like done. You should get the answer through quick manipulation. Okay, no need to verify much. First question is clear. How to do the question really in the examination? If you go by the convention of finding the dimension of H and upside not and substitute, that will be rigorous. You have to always think ahead of time that what kind of quantity we know as force, energy, power, and something nearby. Anyway, I hope this is clear to all of you.
Yes, sir.
Yes.
Okay. Okay, next question is find the wavelength of the radiation emitted by hydrogen in the transition of this. This is pretty straightforward. And which formula we're supposed to use? The Rydberg formula, right?
Red bar.
Yes.
So I think there is no need to waste time here. But anyway, just do the question number 3. Just do one part of the question number 2 for your own calculation sake, whether you are comfortable with the calculation or not. Just do it quickly. Just A, B, or C, any part. And I think they have mentioned the Rydberg constant in the header of the exercise. So all values are mentioned there. You can use those values. Done, guys. Question number 2 is over. Match your
Yes.
answer.
Yes, sir.
You should get the answer exactly as
Yes.
given.
Yes.
Yeah. So go quickly to the question number 3. So calculate the smallest wavelength of radiation that may be emitted by the H atom or He plus or Li plus plus. That's very much straightforward. Let's see if you can do the calculation. So to solve question, you should remember one thing. What is SC? How we can you take the value of HC? So it is given to you. So it is basically this
1240.
1240.
12,400.
you must remember the answer actually. So it is 1240 electron volt nanometer. Or you can say 12,400 EV angstrom. Sometime some book will use 375 also. So you can always do your calculation only if you know certain calculation already. Okay, so I think the third question is straightforward. The minimum wavelength means maximum energy, and the maximum is possible when? When it is maximum. It is a Lyman series, right? Not Lyman. It's a from infinity to the first orbit, ground state. Okay. Which means it is equivalent of the positive value of the ground state.
Potential.
No, yeah, you can say ionization potential. Yeah, correct. So for HE, it is 13.6.
Yes.
So the wavelength is how much? Energy is SC by lambda. So lambda is SC by,
Yeah.
and because this is 1240 EV nanometer, and energy we know in electron volt already. So your answer will be
Approximately
nanometer.
91.
Yeah, 91, correct. You can just write nanometer. You can check the answer, and this is how you solve the question. Questions are not difficult, just whether you have the habit of solving question like this or not. That's it. Okay. I hope this is clear.
Yes.
And for HE and LI, you know, multiply with the number 4 times and 9 times. That's the answer. So 91 into 4, how much?
360.
360.
You can check the answer. Is it that?
Yes, sir.
It is above, not 4, upon 4. It is upon 4.
It should be
right?
upon 4, right?
Yeah, because we are talking about the wavelength. Energy is 4 times. So I have to put 4 here. So the answer will come 4 times. How much is that roughly?
Approximately 23.
23.
Whatever. You can do the calculation. You can check the answer accordingly. Okay, third is done. Let's go to the next question. How many of you are still not comfortable with solving question? Tell me. More than knowledge, what is the word is? The way of solving question. Leave the 4. Find the binding energy. What is the meaning of binding energy? Guys, tell me.
Electron.
Total energy.
Correct. So binding is total.
3.4.
So we know the answer. How much?
3.4.
3.4. It's n equals to 2. Yeah. Correct. Mhm. So is it minus or plus? The answer will be
Negative.
plus. Binding is that is bounded by the minus energy. So to break it down, you have to give that energy.
Okay.
So it is the negative of the total. Binding energy is what?
Negative of total.
Negative of total. So because you have released that energy to be part of that atom and that orbit. So once I give you back, you will be free from the atom. Okay, then this is a ridiculous question. 6. 7th question, solve it. So how to solve question like this? You have to find the energy first of this wavelength. So energy of the wavelength is how much? This is question number 7. SC by lambda, because lambda is given. SC is how much?
1240.
Upon
1025. In
now you can use calci, tell me the answer, or you can do it without using calci. So I think it is something close to 2 point something. How much? Sorry, I mean
12 point.
yeah, let me do this calculation. 1240. Yeah, it's a very nice answer. 12.09. Do you remember this answer?
Oh, yes. And from 1
1
to
to 2.
3.
1 to
3.
1 to
3.
3.
1.51. Remember 1.51.
Yes.
So that's why I said these values are very, very important. You must remember.
Yes, sir.
So it is 1, 2, 3. This is 3 to 1 transition, right? So question was, what are the quantum numbers of the states involved in this transition? Answer is 3 and
1.
1.
1.
You can check the answer.
Yes.
Okay. This is again direct formula based. What is the eighth answer? Tell me quickly. Find the first excitation potential of He plus ion. Excitation potential.
4 into 10.2.
Hmm?
Hydrogen into the Z square. Hydrogen का
हाँ,
total
उसका 4 गुना.
charge.
So we have to find the answer in electron volt and remove the electron because we want volt. Understood? The answer we are looking for is in volt, isn't it?
Yes, sir.
Okay, so you can do this directly. So the first excitation potential for H atom is how much, guys? 10.2 eV.
Yes, sir.
10.2.
That is for the H atom, right? So for
Yes.
helium, it is what? Z square
Into 4.
into 4, if you remember. So 40.8 is the answer.
Yes.
See, these all are like formula based on. Okay. A group of hydrogen atoms are prepared in N4 states. List the wavelengths that are emitted as the atoms make transition and return to N equals to 2. Tell me the answer. From 4 to 2, what are the possible ways?
4 to 3,
4 to 2 or 4 to 3 or
4
then
to
3
3,
to
4
2.
to 2.
This and this. So there are three possible answers, right?
Yes.
Yes.
So
N in plus 1 by 2.
3.4. So what are the possible difference? 3.4 and 0.85. How much? What is the difference here?
10.2.
Tell me all the three difference, and because for every difference, we apply to SC by lambda. SC by E, that is lambda. So HC is 1240 EV NM. And the E we can attach 3.4 minus 0.85 and 3.4 minus 1.51 and 3.4 minus this is done. Done. So 1.51 minus 0.85. You can check the answer. This should be the answer. Understood the idea? How to solve this?
Yes, sir.
The number of wavelengths will be 3, and for every wavelength, you can find the answer by taking the energy difference and putting into the formula SC by lambda, SC by E. Lambda equals to SC by E. Tell me if you're getting the answer, yes or no. Answer matching, guys, tell me. So I think I'm getting first on 656 nanometer something. The first answer. Check the answer. 9.
Yes, sir. 656. I'm good.
Yeah, so that is one answer. Other answer can verify. Okay. Another is 486. Also, there is the answer 486. You can check. There is 486 is the answer. Tell me, guys, yes or no.
Yes.
And one is coming 1878 something. You get the answer. Yeah, I may roughly say because we have taken 1240. Yeah, I mean close answer. Fair enough. This will work. Yeah, just because you can take 1.5. 1.51 is not, they are not taking 1.51. You just take 1.5, then you will answer match. Okay, fine. I hope you all understood how to get this answer.
Yes.
Yes,
Understood.
sir.
Any doubt in this? Tell me, guys. Anyone?
No doubts.
Okay, fine. Then 10th is easy only. That's again very simple. 10th question, you can find the answer.
Yes, sir.
Yeah. So I think ionization energy, you can find the answer directly, right? So 228 will give you the ionization energy. How much it is coming?
54.4.
Yeah, 54.4. And if I divide by 9,
Yes.
16. Okay, so it is a what? So it cannot be H atom, right? So
It's
it is
13.6 into Z square. So helium. It should be helium.
HE.
helium. It is helium,
Yes.
definitely it is helium. That's then only it is possible, no? 13.6 into 4.
Yeah.
Now these answers are very typical, and anyway, see, we are supposed to only guess the 4 answers. H, He plus, Li plus, B plus. So anyway, you can check the answer. What is the answer given? That only, right?
H.
He, helium, no?
Yes.
Helium. Fine. Anyone who has not understood this question, tell me. Raise your hand. Okay. Find the maximum Coulomb force that can act on the electron due to the nucleus in hydrogen atom. Tell me.
Find the maximum.
Force. So maximum force means what? The electron must be in the ground state.
K square by A naught square.
Yeah, so K is square by K Z is square. Oh yeah, this is yeah. K
K
is square
Z
by
is-
K is square by A naught square.
Yes.
And I think A naught is given to you.
0.53.
Point it's known to you 0.353 angstrom, right?
Huh.
So substitute the value, tell me the answer. Again, let me tell you, the calculation is more important than knowing the value, because you will make mistake in doing the calculation. And you are not supposed to use the calculator. So make sure that you are using the simple calculation to get the close answer. Okay, anyway, that's a question from electrostatics, so we can ignore. Question number 12, quickly. I think again this is very easy. Once you read the value, you can understand. This is pretty straightforward. So anyone who is getting the answer, there is no need to solve, you can answer directly.
Oh, yes, sir.
Yeah.
I think it first will be 4 for 0.85 and then 2 for
Yeah.
10.2.
Correct. This is the first excitation energy.
Yes.
So, so it is 4 to 2, right?
Yes, sir.
You can check the answer. You can check the answer. Same answer?
Yes.
Yes, sir. 4 2.
Do you realize that what is the importance of knowing the values? Okay, so if you remember in the first lecture, we were memorizing the values, n1, 2,
Yes.
3, 4, 5. Because if you don't memorize, it is difficult to do the calculation faster. Okay. So you're not supposed to use the formula every time, then get the value of each orbit, and then let's say if you're solving question in examination, and if you don't remember the values which we talked about in the first lecture, what we will do, make all the energy values, write on a paper, then start solving. Okay. Anyway, 13 question. I think that's very easy. What is Balmer series?
N to 2.
Correct. So whenever a photon is emitted by hydrogen atom in Balmer series, it is followed by another photon in Lyman series. What wavelength does this latter photon corresponds to? So Balmer to Lyman means where to
2
where?
2
2 to?
1.
That's it, simple.
2 2.
2 to 1.
Yes.
See, for Lyman, we need to come to 1. And we have to come to 1 after Balmer is released. So we have to come to 2 first. And then we have to go to 1 to get the Lyman. So 2 to 1 is, that's a known value. So 10.2. So the wavelength will be 1240 by 10.2. How much? 124 something. 121. How much?
Or 912 into 4 by 3.
13. Yeah, it's roughly 122. That's logical. 124. Sorry, 1240 by 10.2. Okay. Anyway, the next part. Oh, is this clear to everyone? 14 question.
Yeah.
Yes.
Any doubt in this?
No.
Okay. So 13. This was 13. Now solve the 14. Solve 14 quickly. So by writing the energy diagram, you can get the answer directly, isn't it? So 1.13 EV, where to where?
6 to 3.
6 to 3. So value is okay. You can start from 13.6, 3.4, 1.5, 8.5, then 5.4, then 3.7, right?
3, 7.
Yes, so 1, 2, 3 to
So I think this is 1, 2,
Yes.
3, 4,
6 to
5,
3.
6. It is 6 to 3 directly. I can see the value,
Yeah.
right? Okay, so that is done. So find the energy of the photon emitted in the second transition. So you make only 2 transitions. So then next is here only. That's it. How much?
Yes.
12.09,
12.09. Yes.
1240, roughly 101, something like this. How much? How much is the answer? 100 point something? What is the answer?
Sir, we want the energy only, not the wavelength.
Energy. Yes.
So energy is this much one, I think. 14.
12.0.
14 answer is 12.09. Yeah, correct.
Yes.
So it's simple. No? Is it difficult?
No.
And what is the value? So that's why I'm saying, if you want to solve
3.
Bohr's theory, simply remember the energy values. You can see what is happening. Okay, guys, I hope this is clear. So 15, what is the energy of H atom in the first excited state of the population to 0 in the current state? Yeah, tell me the answer. What is the energy in the first excited state if the potential energy is taken to be 0 in the ground state? What will happen? If it is 0, then answer will become positive or negative.
Positive.
Correct. You have to just reverse the
So 2
sign.
plus 20.4.
Yeah, maybe. What is the potential to be taken? Sorry, what is that? Okay, so n equals to 2. N equals to 2. How much? You take infinity to be 0, right? So when you take infinity to be 0, and they're asking only potential, right? So only potential will be twice of the total.
Total.
So the difference is how much? 10.2.
10.2.
Because you're coming from the other side. Okay.
Yes.
So
So total should be
if
plus.
the, yeah, so of course it will be plus only. So the answer should be 10.2. You can say 20.4, no? Double. The potential is double. You can check the answer. How much?
It's given 23.8.
23.8.
23.8. Where is the, okay. So we have to subtract first excited state. This is 0. Then we have the negative answer, right? And now what they're saying, if we switch it, if this is 0, if ground is 0, then this will be how much? This is the question, right?
Yes.
Okay. So now infinity is 13.6. Then only this is 0. Okay. So calculation will change accordingly. 23.8. How to write it in the reverse order? Zero. Okay.
So
13.6.
reverse will subtract everything from 13.6, right? That we will get the.
Yeah, exactly. Yes. So this will become 10.2.
Yes.
Next will become similar 12.09.
12.0.
12.75. How much? 3.4. So 13.6 minus 13.6 is 0. Then 13.6 minus 3.4 is 10.2. 13.6 into this 10.09. Okay, fine. And this is the right way. So this is the total energy. And they're asking the potential. So it will be double 20.4. Potential is 0, not the total. That's a mistake. No, but that's fine. No? Double of half of potential is also total. Potential is 0, so this is half. Or if you take the
But the electron still has kinetic energy in the ground state, right? Even though the potential is 0.
it will have kinetic energy. So the
So
energy
the
will be
relation
there.
will not hold. We'll have to find a new
Yeah.
relation.
Correct. 13.6 is the, so this will become total. If you make it positive, this is kinetic energy. This is kinetic energy, right?
Yes.
And potential is double with negative sign. Positive sign, it's becoming 0. But whatever be the process, the net should be same. So to get the minus 3.4, this must be how much? But this is plus, okay. Potential. This will be how much? Kinetic remains same actually. Potential we write as with minus sign. Okay. 0. Potential is okay. Fine. So if the kinetic is this much, what is the actual potential in the beginning? Because we need 13.6 as total. So what is the answer here? Minus of double of this value, 2 times of this. Minus 2 times 3.4. This is the potential in the beginning, right? Minus and so on. This is the potential. And now you are making this as 0. You have to add this value to everyone, right? So 13.6 into 2 is how much? 27.2. Correct? So add add 27.2 in every term. That's it. So this is 0 now. This is 27.2 minus 6.8. Minus how much it is? Yeah, minus 6.8 only. How much is coming this one? 27.2 minus 6.8 is how much?
20.4.
Hmm?
20.4.
24.
20.
20.4 only. That's same thing. Question is what? What is the energy of the H atom first? Achha, they're asking energy. So they're asking the energy in the. So energy means total energy, no? Energy means total energy.
Yes, sir.
So yeah, no, not the potential. That asking total energy. So total is how much? 3.4 plus
20.4. 23.8.
that's correct. No, we are getting the same answer. So we are getting this answer as potential and kinetic. We have to also add.
Yes, yes, yes.
If this is 0, so we are okay. We were writing only potential part, and now we have to also add the kinetic part because they're asking the total energy. Okay, in the beginning I read this as only potential. So what is the energy of H atom in the first excited state if the potential is taken to 0? Okay, I hope this is clear.
Yes.
Once again, you can add the potential. This if this is 0, this will be how much? 10 point. How much it came? 20.4, 10.2 into 2, right? And so on. And then the kinetic remains same because kinetic will not change. I keep on adding, look at that. So kinetic is how much? The positive of the total, if you remember.
Yes.
So positive total is kinetic energy and the potential is double of total. So that is how you can do the calculation. Okay, anyway, next. Question number 16. So you can underline the question number 15. This is a nice question. Question number 16 you can solve now. So anyone having doubt in the 15 question, tell me. Do you need to explain? Raise your hand if you think you need more explanation. 16 done, guys.
Doing it.
Okay.
Done, sir. 16.
Done. What's the answer?
Yes.
27, 12 and 27 and 12.
27 and 12. What is that? Energy.
Energy of the ground state is 27, minus 27, and energy of the first excited state is minus 12.
Okay. 16. Yeah, that's the right answer. So you all got the answer?
Yes.
Everyone.
Yes.
Okay. Then gas is- okay, so I think you got the some momentum to solve the question. So we can go directly to. So those I'm not solving, you are supposed to solve at home. Find the maximum angular speed of electron of H atom in stationary orbit. What is this? Simple question. Okay, I think solve. Can you solve the question number 19? Can you solve the question 19?
Yes, sir.
That's interesting. Let's see. So 19 and after 19, you all are supposed to solve. Comprehension 18 to 20, page 23 of the sheet which I have shared. Okay, I'll be back in 5 minutes. Section done, guys. Yes, so my question number 16 is over.
Yes, sir. We're on 19. Huh?
Okay, 19, yeah, 19. Okay, so this is the question, same question which we solved, in which we found the wavelength when n is very large. Okay. First of all, you need to understand the question first. What is the meaning of question? So we are supposed to find the biggest value of n. So let's see if you go from so this will create a wavelength. Okay, so what they're saying can resolve two nearby wavelengths such that the wavelength and the difference. So for the wavelength and the difference. So if you remember that, what was the formula for the transition like this? If you remember, tell me, guys.
Two R
So for H
Z
atomic
square
mass,
by N cube.
yeah. So you're coming to Balmer, no? So you can this is Balmer equals to 2.
2.
So if you differentiate, what you can get? Not like this, just a bit. So it will come minus 2 dn by n. Is this correct?
Yes.
Just check if this is correct or not. So n is really large. Okay. So it turns out to be how much? So we can take dn. Okay, I think we have to differentiate this with respect to n. So minus 1 by lambda square d lambda by dn. I can write like this. R into minus 2 by n cube. Yeah, this is better of writing. Okay. And d lambda by lambda square is n cube. And we can take dn equals to 1 for the two consecutive transition. So 2 lambda by n cube. And this is less than
800,000.
8,000, right?
Yes.
Okay. And if n is really large, this is roughly equal to what you can write? R by n square convert like this? Tell me guys, yes or no? Sorry. If n is really large, then this is roughly equal to? No, it's other way around. Right. So 1 by n square is 1 by infinity. It's roughly tending to 0.
The formula will be 1 by 2 square minus 1 by n square, right?
Yeah, that's right. That's a mistake. No, that's let me change this here. So we are coming from up to 2, right? If n is really large, then this will become, so 1 by lambda becomes n tends to n is much closer than 1. R by 4, right? Lambda is 4 by r. So we can substitute here. Na? Lambda r is basically 4. So 8 by n cube is less than 1,000. So n cube by 8 is what? Something you can just see if it's wrong or something. What I'm doing. So this is 1,000. Oh, sorry. It's other way around. Lambda by delta lambda is 1,000. Na? Just check the inequality. Anyway, we got the idea. So what is given is lambda by delta lambda is, okay, I wrote other way around. So n cube by 2r lambda is less than 8,000, and then we know the lambda into r is 4.
So what is dn?
dn is the transition, like n to n minus 1. This is
We're
dn.
transitioning from n to 2, right? Because it's specifically
No. We are solving for the case that if the smallest wave, I mean the difference, as we go higher in the orbit, the difference will almost merge, isn't it?
Yeah.
So what is the smallest difference that we can resolve? So a spectroscope is a device which can differentiate between the two nearby wavelengths, nearby. That's called resolution. It is
dn
like
corresponds to delta lambda.
Yeah. So dn is basically the nearest to orbit you can think of. 1.
Okay.
Yeah. So this turns out to be how much? N cube is less than 6,400, right? So n will be how much? I think 40. No,
sorry, it should be 61,000.
64,000, yeah. So this is 440, no? 40 is correct?
Yes.
Yes.
So the Balmer series means what? 40 to 2. So how
Yes.
many spectral lines are possible then? How many? N2 minus N1 plus 1 C2.
And not all
Okay.
possible. We need only the Balmer. So that will just be
Yeah, so Balmer means what?
37.
Yeah, so we have to go to Balmer means how many? Yeah, 42 is 2. So everything should come to 2, right?
Yes, sir.
So from 40 to 2 to 3 to 2.
Yeah, the last will be 3 to 2.
So 38, na? How 37?
How many? 38,
Right,
no?
30.
Yeah. Okay, we are not supposed to find all the transition. Only the Balmer one, correct. So
38.
only Balmer will be how much?
38.
38. 38 or 37, something like that.
38.
Okay. And what is the answer given? 38 is given. Yeah, correct. Okay. This is the easy way of doing. You can also do by the same finding the two wavelength nearby wavelength. So you can substitute here only n minus 1 and then use the binomial approximation because we are going to assume n to be really big. I have the concept is clear to all of you. What is happening here?
Yes, sir.
Yes, sir.
Yes.
This is slightly challenging because we are using differentiation in Bohr's theory. Anyway. The next is suppose in certain condition. This is nice again 20. This is something interesting. Can you solve 20? Then we'll go to the JEE question after this. Done, guys. So suppose which question?
Sir, part A. do.
Part is done.
Yes.
Yes, so
Suppose
same.
in certain condition when those transitions are not have change by 2. Okay, fine. That's what's it. Okay, fine. So just 2 means what? 135, right?
Yes.
And the answer must be in between 380 to 780 nanometer.
Yes.
Yes.
Yeah, so I think condition is given to us. So the A part is done. The smallest will be where to where? The smallest
3 to
will
1.
be
2 1.
yeah,
3 to
that's it.
1.
That's it. No, it's just wavelength, no? Just a minute. The smallest wavelength will be
Highest energy transition, no? So 3 to 1.
Why not 5 to 1? Why not 7 to 1?
Because there should be only a difference of 2.
Is it written?
Only those transitions are allowed in which the principal quantum number changes by 2.
Ah. Condition is given. Yeah, correct.
Yes.
Is the answer matching?
Yes.
Yes, sir.
Correct, correct. Yeah. So we can have either 3 to 1 or 5 to 3 or something like this. And the biggest will be 3 to 1, the nearest one. Correct?
Yes.
Yeah. And then you can do the range question. That's simple, I think.
Sir, why never? Like, is there an easy way to do that? How do you find which wavelengths lie in this range?
Okay. So you can do like this. What is 380 means? Nanometer. What is the energy difference? Delta is how much? 1240 by 380 EV, correct?
Yeah. 3.2.
How much? How much is coming? Tell me.
3.2.
3.2.
Yes.
Okay. Just confirm. Yeah, 3.263. 3.263. So when it is possible? 3.4, and we have to subtract something. Okay. Then 27, 27, 26. So which wavelength? Okay, which transitions are possible? So this is possible, this is possible. But okay, no. List the wavelength emitted by the H atom in the visible range. So the maximum difference we can have is 3.2. Okay. Fine. The maximum means that is the difference. So, and the minimum is how much? $1240 by 780. 1.59
Close to 1.6.
roughly. This is the AV. And only those are allowed in which the changes is 2. So this is a big change. We cannot go more than 3.2. So can we go for this change? I think no,
No.
because this is more than 3.2, right?
Yeah. 3.3.
No, this we can go. No? How much is this? This we can go. No? 3.4 and 8.85. How much? So our energy difference will be what is the range of energy difference? 1.59 up to 3.2. So any difference less than this we can allow, no?
Yes.
So this transition is possible, yes or no?
Yes. Yes.
So this is one transition is possible, and only we can go for 2-step, right? We can go 2-step. So from here can go this one. Is this allowed? No. This is not allowed. Why? Because this difference is less than 1.59, correct?
Yes.
Yes.
So I think only one transition is allowed, isn't it? This one. No other transition you can see because the difference is only 2. Only those transitions are possible in which the difference is only 2 steps, right?
Yes.
So this transition is 3.4 minus 0.85, which is 2.55. So the wavelength is how much? 240 by 2.55. This should be the answer. .486 nanometer, roughly. Any other transition is possible?
No, sir.
No.
No.
Check the answer. What is the answer given? Is it list?
Yes, sir. Just this one.
This one, no? 486. Yeah, that's correct.
Yes.
Yeah, only one is possible. There is no other possibility. I hope this is clear. Only one
Yes.
answer is possible,
Yes, sir.
isn't it? The answer, which is 1.59 to 3.2 electron volt, and we know that that range is coming only once. I mean, there is no other possibility. Anyway, so it's all about energy difference, which you have to see and solve. Okay. Okay. Okay, so I think we should go back to the JEE problem. Rest you can solve at home. If you keep on solving everything here, then it will take too much time to finish modern physics. So you all have received the sheet, which I have shared just now.
Yes.
Yes, sir.
Please open it. And go to page number 23. So are you all at 23?
Yes.
The 23 of the PDF or of the sheet?
PDF. I mean the sheet, actual sheet. 23 of the sheet. Yeah.
Okay.
You can see a comprehension 18 to 20.
Yes.
Okay, so
Yes.
your job is to read the question and solve it. That's very difficult job, but you can do it. And the last concept that we studied in the Bohr theory, you can see why it is there.
So question number 18.
19 and 20.
Okay, 19 and 20.
Yeah. 3 questions are there, right? Comprehension.
Yes.
If you look at the heading, it's written comprehension 18 to 20, right? Okay, so read it. Not very difficult, I think. So this is the rotational problem that we just solved a while back. For modern physics, you can start with SU Verma. That will give you the initial boost in terms of thinking and solving. And then go to the JEE PYQs, because PYQs are very, very important because not everything is covered in SU Verma. So I'll cover some more concept in Bohr's theory, then I'll go to the next topic called X-rays, which is really interesting. So I expect that, okay, you all have studied photoelectric effect in chemistry.
Yes,
You all
sir.
know photoelectric effect, you know about it, right?
Yeah.
Yes, sir.
Yeah, fine. Because X-ray requires that idea. So the name for the X-ray is called the inverse photoelectric effect. Question is clear, first of all. Tell me, guys, if the question part is clear, what we are supposed to do?
Yes.
All right, then you can solve. And they have expressed the answer in terms of moment of inertia, so no need to substitute mu and all. You can simply write I. Okay.
Yes, sir.
All right. Tell me, guys, if it is done. Then
One minute.
Sir, I'm not getting the 20th question.
20th question.
Last one of the pair.
Use the quantum. Okay. You have to relate the distance, right?
Yes.
The radius in terms of principal quantum number. So can we relate the distance with energy? You can use the circular motion to get the formula, right? Hopefully, you should get the answer energy and momentum. I mean, this in
Yeah.
terms of distance. Hopefully, you should get the answer. Let's check it out. The Bohr's quantization theory is applicable, right?
Yes.
The rotational kinetic energy in the nth level is. So you got that in part?
Yes.
Everyone?
Option D.
Option D. Yeah, NH by 2%. Okay. Let's see if this is solvable or not. Josh, you got the answer for 20th?
Yes, sir.
You got the answer. Which answer?
C.
So how you got the answer? Explain to everyone. Explain.
Just explain as in मतलब
What equation you wrote to get the answer? Send me your solution. Let me see. Darsh, you got the answer to the C part, 20th part?
No, sir, not yet.
Okay. Anyway. So the key feature of Bohr's theory condition So the first part is, I think, the L equals to NH by 2 pi. And what is L here? What you can write L?
I omega.
Yes.
And then substitute it in K.
But even in fact, this is not required because you know L, so we know the formula energy equals to L square by
L square by 2i.
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 Yes.
If you remember, we have done this before.
Yeah.
Yes.
So 4 to the 8. This was the answer, right? With minus
Yes.
n, of course.
D.
So, but they're asking the rotational kinetic energy. So this is the kinetic energy, which is simple formula. You can write like this. And what else? So potential energy is how much? Potential will be how much? It is found by and then okay, the energy of excitation from ground state to the first state. So you know how to find the energy of excitation, right? So the total energy will be how much? Minus K, right? Obviously, you can find the delta. I mean, this is a delta of K. So what you get? N. Anyway, you can just find the difference of the two. Why to write this? So N is square, you can say 1 to 2, 2 is square. This 1 is square. This is delta K.
3 by 8.
3 by 8. And this is given, no? How much? This is given in the question, I think. Hmm. 4 pi by, so we can attach HF, right? This is what you did, no? So the energy difference equals to H into F. We can write like this directly,
Yes, sir.
because the delta KE and delta E will be same, no? Numerically.
Yeah, numeric.
Yes.
Both are same numerically. That's why I'm saying. So that's why we got the delta K and we got the answer. So I turns out to be how much? 3H by 8 pi square F. 3H. Pi square, I can take 10.
Pi
Because they have
square
given the
10,
H
yes,
value.
yes.
Pardon?
They have given the H, like,
They've
so
given us.
then the pi will get cancelled.
H you can use as 2 pi
Yeah.
into 10 power
Okay.
minus 34. So
Yeah.
pi will get cancelled.
Whatever they have given, you just substitute. I
Yeah.
haven't seen that answer. So 3 by 8 into, they have given something 2 pi into, right? 2 pi into 10 power minus 34. Correct?
Yes.
And this is pi square, and frequency given is 4 by, all pi gets cancelled, right? Nice value.
Yeah.
So 16. 3 by 16, 10 power something. How much? Right? Sorry, minus 44, no? 45. Minus 45. How much is coming? 30 point 1 point. How much is coming? Tell me. 9 something, 1.9 something, right? Minus 6. B, no.
Yeah, option B.
Option B is close, right? No,
Yes.
correct.
Correct.
B is close answer. What is the answer given? B only.
B.
Very good. And in the CO molecule, the distance between C and O is close to. Okay. Distance.
We can use what we say, once we get the I, we can use two equations, like we can substitute C as M1 R1 square plus M2 R2 square, and you can substitute R1 and R2 in terms of their masses, like M2, let's say their distance be say D.
It's simple, na?
That reduced mass, directly you can use reduced mass.
Very good. So moment of inertia is how much we got? So we got the answer moment of inertia 1.87 given. And the reduced mass you can get from the values given. And that is 12 into 16 upon 12 plus 16 in AMU. Then you can convert into that. So 12 into 16 upon 18, right? 28. 12 into AMU, which is 5 by 3 10 power minus 27. 80 by 7 minus 27. Oh, you can do the calculation. I think you should get the answer. How much is that? You have to be very careful because the values are very close. Okay.
I guess 1.3 something. It is the closest one.
Yeah, you have to very carefully here by yeah, okay, 0.16. This is 0.4. And this is how much? 10 46 minus 26, 46 minus 27.
19.
19. This is 6 minus 19. It is 16 to 10 power Okay, anyway, will not work. So that you can add
minus 21 because
1.6 into
or
10 power.
power
1.6 into 10 power. Sorry.
10
not
minus
1.
10 minus 10.
Yeah, minus 10. That's fine. Yeah. So 1.6 is how much roughly? Less than 1.6.
0.414 is
1 point
1 point
You can say 1.2, no? 1.2 more than
1.2 or 1.3
1
we can
point
say.
3 between. So 1.2 something. So you
Yes.
can see
So option C.
option C is nearby, no? Because
C.
close to, yeah,
Yes.
close to is fine.
हाँ.
Yeah. Yeah, C should be the right answer. You can check the answer. Okay, so you can see the application of the reduced mass, right? Luckily, we have one question that we can practice. And this all reduced mass thing will come in J advanced one. Okay. Solve question number 27 of page 24.
That is multiple correct, right?
I don't know. You
Yes,
solve with an
because asterisk
Yes, it
is
is.
R. Yeah, is R. Yeah, so maybe. Solve 27. Okay, everyone got this idea, this answer? I hope
Yes.
so. This is clear.
Understood.
Yeah, so nice question with application of rotational dynamics, Bohr's theory. Okay, and you can see the benefit of reduced mass. Everything in two particle system becomes reduced mass concept. Okay. Solve the question number 27. See, after this, I'm going to teach you something. So this will be the last question for today. Rest you have to practice at home because we cannot solve every question in the class itself. I hope you can understand. So this is just for your flow. Like once you get the flow here, then use this flow to solve at home. So you got the idea that how things move and how to apply various relation. Good, very good. Okay, so can we go to the next concept if you are done with this question? Seems easy only. I hope you can do this.
we can directly use energy by 2 pi.
Yeah.
Yes,
And
so
get
got
10.
the answer.
Yeah, correct. So let me teach you the remaining part which we haven't taken care of from the Bohr theory. So today I have to finish the Bohr theory completely, and next lecture will be X-ray, and the next will be nucleus. So the next part is called collision of atom with photon. Okay. So collision of atom with photon. So energy we can attach for a photon, h nu or sc by lambda, correct? And momentum of
Yes.
momentum of any EM wave we write as energy upon speed of light. Okay. So momentum is also associated with any massless particle. So photon will have zero rest mass. So when I say massless, it means we are talking about the rest mass. But we do have something called the relativistic mass. Okay. So you can equate this with mc square, and then m will represent the relativistic mass. Okay, so that is what you can do for convert energy into mass equivalent. Okay, but that is definitely not a mass. And this relation I have derived in electrostatics. So it comes from the Einstein theory of relativity. So we know that the moving particle will have a mass equals to rest mass upon 1 minus v square by c square. And we know that this term is called the relativistic mass. And this is called rest mass. So once again, you can do this. So the energy associated with any moving particle is basically mc square, which is basically m naught square c square upon 1 minus v square by c square. This is how you can write this formula. And momentum we can write as mv, but m we can also write as m naught v by. So p square we can write as like this. And okay, so what we can write is, if this is p square, this term called p square c square. What is p square c square? You can check. Okay. And oh, this is mc square. What I did? Oh, I made a mistake here. It is m square. I want to write m square. Then this will come power 4, right?
C power 4.
Yeah, rest is okay. Yeah. So if you add the value, that's very interesting. If you add the value of what? This is question 1. E square plus, okay. If you look at not add value, E square is how much? We got the answer. M naught. So I want to write. Okay. So basically, the P square C square. P square C square, we got how much? Just take me out. M naught square V square C square by. Okay. I think this is right. And if I add these two terms, let's say I'm adding m naught c power 4 plus p square c square, how much we are getting if you add this value? So we can take common. What we can take common? M naught square c square, right?
Not for C square.
So what we are left with? C square. So if you multiply, if you take LCM, just time pass. Okay, so what will get? Something really interesting. M naught c square, and this will become c square plus minus v square plus v square, which is c square again, right? Can I simplify it like this?
Yes, sir.
This is m naught square c power 4 by. And what is energy? You can see it's equation 1. No? So this represents. So the energy and momentum we can relate like this. This is the energy and momentum relation, which you must remember. Easy to remember. E square is PC whole square plus m naught c square whole square. So this is the energy relation in the world of relativistic. Okay. So this is the in general for every moving object. This is the energy. So it does depend on momentum, but energy is also associated with massless object like photons. Okay. So for photon, what is zero? The rest mass is zero.
Rest mass.
They don't have the rest mass, and that's why the relation becomes E square equals to P square C square. Basically, you can say E equals to PC. Correct? Yes or no? And of course, don't worry about the derivation. This is I'm doing just for the sake of writing, so that I maintain my practice. So E turns out to be PC. That's why the momentum formula is energy upon C. This is the formula for momentum for every electromagnetic wave. This is the actual formula. Okay. So you can also say if any wave carries energy D, it will have the momentum equals to energy by C. This formula we are going to use a lot in the chapter of electromagnetic radiation pressure. But anyway, for Planck's, according to Planck's law, the momentum current is energy E by C. E itself is how much? H is SC by lambda.
Yes.
Or you can say H nu by C. So that's why you can see the formula H by lambda. So the momentum associated with any electromagnetic wave is H by lambda. And the de Broglie said the same thing, that if electromagnetic wave can exhibit momentum, which is like a particle-like behavior, so the reverse should also be true. So you can say a moving particle can also exhibit the wave-like behavior. In that case, you take the property momentum as the particle behavior and you convert it into wave-like behavior to bring the de Broglie wavelength or de Broglie wavelength. So you write H lambda d equals to H by P. Understood? So this you also write as H by mv, and you can also write this as H by under root 2 mk kinetic energy. Okay. And this is really interesting. For a particle, the energy we write means kinetic energy. For electromagnetic wave, the energy is hc by lambda. So if there is a difference. When we say particle energy, we cannot write hc by lambda de Broglie. That's wrong. Okay. So energy of particle should not be written as hc by lambda. Energy of you can say EM wave. This is correct. So energy of particle basically means you can say kinetic energy of particle, and this you can write as how to write half mv square, or basically you can get the answer from here. So de Broglie wavelength, if you write so 2mk is how much? So given the de Broglie wavelength, what is the kinetic energy? So that's why the energy when you write for particle, the formula should be changed. It will become like this. For EM wave, this is correct. For a particle, we don't write. Rather, we get the momentum to derive the wave equivalence, the de Broglie wavelength. So the de Broglie wavelength is a really complex topic. If time will permit, I'll discuss about it. Okay. But you should know the formula itself. That's more than sufficient. So I'll finish this part of de Broglie quickly. De Broglie you can write as H by 2mk or H by mv, H by p. So for gas, what we write? What is the most probable velocity? Right. So the majority of the particle will have this velocity, isn't it? So what is the de Broglie wavelength associated with the gas at a temperature T? MV most probable. How much is that? 2mkt. Okay. So for different scenario, if you know the velocity, you can express the corresponding de Broglie wavelength. Okay, anyway, this is not our discussion. So I was talking about the photon. So a photon represents what? An energy packet, right? So photon basically means quanta or packet or whatever you can say. So this finite energy, which is carried by photon. So the rule is photon cannot, kind of give away its energy in fraction. Okay, when it comes to atom. So atom cannot take the fractional energy from photon. It will either take the all of or none. Okay. So for atom and photon interaction, the rule is all or none. What does it mean? If the energy of photon is equivalent of the energy difference of any orbit, and if there is some electron in that orbit also available, that photon will be completely absorbed and it will be used for the electronic transition. Okay. Now the question is, so what will happen to the conservation of momentum? Because a photon is carrying momentum, and if it is absorbed, then momentum becomes zero. So isn't it the violation of conservation of momentum? The answer is no. The atom will start moving, but the atom is really heavier mass compared to the photon, and therefore the energy required to maintain the momentum by the atom is really negligible. So it is like a assumption that nearly all energy is consumed in the excitation. So 100% energy is wrong idea. You can say 99.99% energy is consumed, and then a part is required to maintain the momentum. So atom will take that energy, will move and will conserve the momentum. So that idea is always there. Okay. So when we solve question, of course, I'm talking about the numerical part. The momentum consumption will be there, but to solve question, we will assume that all energy of photon is going to be absorbed by the atom. So when all energy is absorbed by the atom, then the collision is said to be
Inelastic.
perfectly inelastic.
Perfect.
Yeah. The moment energy difference of any two orbit is not matching the energy possessed by the photon, incoming photon, then it will be reflected back. That's called reflection. So in that case, photon will not at all interact. It will come and go back. Okay. So now the energy of photon, if not equals to the transition energy from one orbit to another orbit for the given atom, it will be sent back completely without any disturbance, and that's collision is called perfectly elastic collision. So I hope the idea of collision is clear in this case. So I'll just mention this point. If energy carried by photon is equals to possible transition energy, because I don't know which transition is possible, so I'm writing possible transition energy, which may be 1 to 3 to 1 to 5. So depending on let's say if the atom itself, because every atom will remain in the ground state, okay, even if it will get excited, it will come back in no time. So if the energy of excitation, if it is either E1, E2, E3 or whatever, then it will be absorbed. If it is none, let's say we may have a situation in which the atom goes into some excitation and then a photon is coming, because the first photon excited, then the next photon came, which is interacting with the excited atom, then you need lesser energy to go to the next transition. So that's why I'm saying whatever is the possible transition energy. Okay, if the energy carried by photon is equals to the possible transition energy, I don't know which transition is possible in a given context, but whatever is possibility, if it is equal, then it is going to be completely absorbed. So if energy carried by photon is equals to possible transition energy, then it will be completely absorbed, and atom goes to excited state, or any can say higher excited state. Such collision is called what? Perfectly elastic collision. Perfectly
Inelastic.
inelastic. Just a moment, let me. Else perfectly, or else photon is sent back, photon is reflected back by the atom, and such collision is called what? Perfectly elastic collision. Let me give you the, okay. So in photon collision, what is conserved here? Energy and momentum both remains conserved. Okay, energy means energy in all form. I'm not talking about the kinetic energy, I'm talking about the energy only. So in photon interaction, momentum will remain conserved. So the energy which we need to conserve the momentum part, that is so negligible. That's why the most part of the photon energy we assume going into transition. I hope this is clear. So let's say, let me draw this diagram. The situations we have photon, we have H atom in the ground state, let's say. H atom in ground state. So it will have energy H nu, it will have momentum H by lambda, or E by C or H mu by C too much. Okay, so you can write the way you want. So from conservation of momentum, linear momentum, what you can write here? Tell me. So before collision, what is the momentum? Only h by lambda, isn't it?
Yes.
Imagine the scenario if it is completely absorbed. If photon having sufficient energy to get completely absorbed. Okay. So this momentum anyway, this momentum after collision will happen. This is the before momentum. After collision, whether it is if it is absorbed, let's say if it is absorbed. So okay, I'll take case actually. Case one. I'll take the case first. Case one. For perfectly inelastic collision. For perfectly inelastic collision, what we'll assume? Tell me, guys. The momentum will be h by lambda, and then only atom will move, isn't it? Can write like this: mv. This m is the mass of atom. Okay. So basically, initial momentum equals to mv. What you can say the momentum of the atom. So what is the kinetic energy of atom? So kinetic energy of atom is momentum of atom whole square by 2m, isn't it?
Yes.
And momentum is h by lambda whole square. Are you getting this? So kinetic energy of atom is how much? For the momentum consumption part, this is the part for momentum consumption. But once you're done, you know the momentum of atom, so you know the kinetic energy of atom. H square by 2m lambda square. And if you compare the energy Sc by lambda of the actual photon, let's try to find the ratio, like the energy of photon. I'll take the vice versa. So okay, I hope this is clear. Are getting in doubt here? So Ke atom after collision. Just to give you the idea that why I'm saying this is roughly equal, Ke atom upon E photon is how much? Ke atom upon E photon. So Ke atom you got h square by 2m lambda square. And energy photon is how much? Sc by lambda.
Yes.
So one lambda will cancel out. What we're left with? H by how much?
2m lambda c.
H by 2m lambda. 2m
Lambda c.
lambda c. Yeah, c will come. No? Lambda by c. Yeah. Correct. Oh my God. H itself is very small. C will make it even smaller. M will make it even smaller. Let's do this. So let's say lambda is some visible spectrum. You can just choose some value just to get the idea. Mass of atom, H atom is how much? 1.6 10 minus 27. Okay. And the lambda, if I take roughly 5400 angstrom. And C is 3 × 10⁸. Who is the winner? Tell me guys how much answer is coming roughly. In the power of 10, just I want some order of 10. Hopefully should be negative.
Yeah, it's 10 raised to minus 5 or something.
Roughly 5, no? Very good. I'm really happy. You can imagine that it is the 5th place of decimal. Like the energy difference is on the fifth place of decimal, isn't it?
Yes.
Which means compared to the energy of photon, the energy of atom is negligible.
Yes.
Are you getting the idea? Is it negligible? Yes or no? I mean, see, let me do this calculation if you're not convinced. 6.62. Okay. Hmm. 1.2210 per minus 4. So for 1.22 34 and 27, how much? 7. And this 10, 3 and 8, 5. Minus 9. Oh my God, this is very, very small. It is roughly 10 power minus 10. Understood? This is the ratio. You can check more precisely. Anyone who can re-verify this? What I just said? Anyway, so what I'm saying is that momentum will be conserved. And even though it is going to be perfectly absorbed, the energy that is going to be carried by the atom, the energy is nothing compared to the energy of actual photon. Therefore, we assume that the absorption is of complete photon. I hope this is clear to all of you.
Yes.
No, not clear.
Yes, sir.
In fact, this was the JEE question of 2023 actually. It will come next time. So momentum conservation will take place, will follow everywhere. You cannot violate. Case 2 is not required because I have proved that what will happen exactly. Okay. So if it is getting reflected, it means the atom will go. Okay, so we can also do one thing in quick. Okay, I'll do this first. This is important. Less time particle in a box. The idea of atom or orbit is like a confinement. Okay. So when you say that the electron is in the first orbit, you actually kind of allow the uncertainty in position that electron can be anywhere in the 2 pi r dimension. Okay, so it's like a space, and then you assign some probability of every point of that space, which we call the wave function, which you study in quantum physics basically. So wave function is basically a function denoting the presence of wave, okay, in a given space, and the psi square is basically the value of probability density, the mathematics. Okay, so psi is a wave function because to represent anything having the probabilistic nature, we talk about the wave function, because electron having the possibility to be found in a certain space. Okay, so electron is not located at one specific point. That's why we cannot talk about the electron as a particle. We talk about the wave-like character of electron because it is spread. We cannot see it, but we can say that, okay, this is the point where it is having more possibility or less possibility. So for that, to give the quantitative idea of the possibility, we talk about the psi square, and to represent it, because a wave can have, if you talk about the wave, it will have the amplitude, and amplitude can be positive and negative. And because probability cannot be negative, that's why we need wave function so that we can represent a wave with a positive and negative amplitude. But to define the certainty, or you can say probability, we need psi square. So that's why both are having different meaning. Okay, and both are required actually. So without wave function, you cannot proceed. That's the whole idea. So these all probability is called mathematical probability. So when you call a wave, particle as a wave, And if you talk about the cloud model, that's called the a model of probability distribution, and the orbitals are the space at which the probability is said to be maximum. Okay, that's why we call orbital. Okay, that's the definition of orbital, I think. So orbital is a space in which the probability is maximum, but again, you are not certain about where exactly in that orbit. So you define uncertainty in position. So that's why we have the Heisenberg uncertainty principle. So particle in a box means what? I have you can imagine a string which is fixed between two wall. Okay, and the wall represents, you know what a wall represents? Technically, it represents infinite potential. And infinite potential means what? Infinite energy. So to cross the wall, how much energy the electron needs? Infinite. And because practically infinite energy is not possible, that's why the electron is confined. That's why we call particle in a box. That's a very famous name. So this is potential.
So still the electron can technically cross the wall, right? Through quantum tunneling.
Yeah, because it depends on the thickness. So if the wall is really thin, in such case, after infinite collision, although it can go above it, but it can go through it. That's called the quantum tunneling. And for that, you need to make roughly infinite collision. And that is pretty much required for in the beta decay. Beta can come out of the nuclei, and the nuclei wall will act as the quantum tunneling. So although the beta will not have, a particle will not have sufficient energy to actually leave the nucleus, indeed it is found that it leaves. Okay.
Oh.
So that's called the quantum tunneling effect. Okay, so that is not part of JEE syllabus, so we can avoid. It's good to learn about. It's really nice. So there is called thin wall and thick wall. Okay, so in our syllabus, when I say particle in a box, then wall will be
Thick.
thicker. I mean, it will never come out of it. It's infinitely thick. It means even if you don't have energy, you cannot penetrate also. So there is no question of tunneling because it is infinite, so it will never come out of it. Understood?
Yes.
Anyway, so let's stick to our particle in a box idea. So how to, explain the quantum behavior? So it will be based on the stationary wave idea. So the explanation goes like this. If imagine this is a string, and if you vibrate the string, okay, if you vibrate the string, so it will have various mode of vibration, and there will be some simplest mode of vibration, which is like this. You will have just one NT node and two nodes. This is called node, and it's called NT node. Not this. This is called NT node, but we represent somewhere here. So this is called the simplest mode of vibration, or you can say fundamental mode of vibration. And that is how you represent the lowest energy value. Okay, so mode of vibration represents the energy value. So in the next case, what will happen if you vibrate more vigorously? It will form more loops. So the larger number of loop represents what? High mode of vibration, which means high energy configuration. Okay. Similarly, if you vibrate more vigorously, it will make 3 loops like this. So basically, the idea of loop that we learn in standing wave idea is called mode of vibration. So as the frequency will increase, because normally in Planck's idea also the energy is proportional to frequency. So this is a really nice model. The standing wave model is the best model to understand the quantum effect. Okay. So the loop is representing some sort of discrete energy packets. You can think that way. It's like the string is, oscillating, and one bundle is oscillating with one kind of energy, other bundle is having different phase actually. So if the left will go up, the right will go down, and the adjacent part will always move in the opposite direction. That's the beauty of standing wave. So as the mode of vibration will increase, which you can also correlate with the principal quantum number. Okay. So by definition, the distance between the two consecutive nodes is called lambda by 2. Okay, so if you don't know as of now, just remember this fact that the distance between two consecutive node is how much? Lambda by 2. So for nth excitation, how many node, how many loop we can see? So in the first excitation, we can see there's only one loop, right? Up and down. In the second excitation, we saw two loops, the red one, you can see the red one. And in the third, you can see there are three loops. That's called the green one. So in the nth excitation, how many loops we can expect? N. So given the dimension of the particle in a box, so the dimension of the box, let's call L. Can we write n lambda by 2 equals to L? Tell me guys, yes or no?
Yes, sir.
Now, because here, what is oscillating here? Particle or a EM wave? What is happening here? A particle is confined, right? So when we write lambda, in case of particle, we write lambda de Broglie. Understood? Yes or no?
Yes.
So the de Broglie wavelength for the given excitation state in terms of principal quantum number, we can write as 2L by N. Yes or no? Tell me.
Yes.
Yes, sir.
And de Broglie we can write as H by P is 2L by N. So P equals to how much? P is how much? Tell me. NH by 12, is this correct?
Yes, sir.
Now, luckily, we are able to correlate momentum with the principal quantum number for the particle confined in a box, isn't it? So what is the kinetic energy of this? So we can see, although we started with the de Broglie wavelength, but when it comes to energy of a particle, we talk about the kinetic energy. And the kinetic energy of particle is how much? P square 2m, which is equals to how much? N square H square by 8 mm.
Yes.
Now the question is this particle interacting with anyone? The answer is no. Is this particle interacting with anyone? Yes or no?
No.
No. So there is no question of potential energy. So potential here is 0 because we talk about the kinetic energy only. And that is why the total energy here we can write as K. So this is the energy of the nth excited state, or you can say nth excitation, having formula n square. This was the J advanced problem. So luckily, although it was not taught, but they have given as a comprehension in which the theory was explained. The way I have explained you, the same thing was given in the problem itself. So even those, who have not come across the idea of particle in a box, they can read the question and still solve the question. So there was no difficulty in solving the question. Okay. And there is a complete comprehension. I don't see till 2015, so it may be in 16 or 17. Or you can see in 41 years, you would come across this comprehension. Please do solve that comprehension. Okay. So with this, I'll stop the Bohr's theory. I'll take care of some more concept in the Bohr's theory itself. like scattering formula. I'll also prove the Rutherford scattering formula. So let me write down, which I'll take care. So these are miscellaneous topic which I mean I will take care given the time. So I'll talk about the Rutherford. So some challenging questions can be solved with this idea, Rutherford scattering formula. What else I would like to take is in the Bohr's theory. Yeah, I mean, I have talked about the de Broglie balance, but I'll just revisit this part. And then Davison, German experiment. So I think these three part should be taken care of. And okay, that you can take later on in diffraction. So we have, okay, rest is in diffraction. Yeah. So these three topic I'll just cover in quick in the next lecture, and then I'll go to the X-rays. Okay. So see you in the next lecture.
Sir,
Yes.
sir, this Saturday you are going to start magnetism. For that, you have told me to read HCV, but I forgot to ask you what all part of HCV